In this introductory lecture, we'll see the basic modes of heat transfer, what are the mechanisms by which this kind of heat transfer process takes place, and some certain basic characteristics of these modes. So first we'll consider conduction, then we'll see convection, and then radiation. Now the definition of conduction is: it is the mode of heat transfer in a substance. Here in the definition of conduction, the substance indicates it can be solid, or it can be liquid, or it can be gases. So both solids and fluids actually conduction is possible in both solids and liquids. That you have to remember. So the definition is: it is the mode of heat transfer in a substance by exchange of energy between molecules having more energy and molecules having less energy. That means the mechanism, if we want to see, suppose consider in solids, you know that suppose this is a particle, these are the different atoms or the molecules. Now they are not moving within the solids. These atoms are not continuously moving within the solids. But in case of gases, you know, in case of fluids, either liquids or gases, you know that the molecules or the atoms, they are continuously moving within the fluid. So in case of solids, the mechanism of conduction is like this. In case of solids, they are basically vibrating. So at each position the atoms are actually vibrating continuously. So because of this vibration, or because of the state of this particular solid, the energy is associated with each of the molecules. And when this particular molecule transfer energy to its nearby molecule, and then again it transfers energy to its nearby molecule, and in this way from one position to another position energy is transferred. But remember always, the energy is transferred from the molecules having higher energy to the molecules having lower energy. Okay, and the process by which it is transferring is basically the conduction. That means they, in case of solids, they are actually vibrating with respect to the mean position. In this way they are interacting with the surrounding molecules, and that again transfer energy to the next one, and that again transfer to the next one. But in this process, these individual molecules are actually not moving from one place to the other place. So this is what is the mechanism of heat conduction takes place in case of solids. This is one of the way by which the heat conduction takes place. The another thing you can say, not only the vibrational energy that transfer from one position to the another position, or from the one molecule to the another molecule, along with this there is another way by that also the solid can conduct, and that process is by the free electrons. In case of metallic solids, you know, the free electrons are available. Free electrons are available in case of metallic solids. Remember, these free electrons are not available in all the solids. Only in metallic solids, you know, the free electrons are available. So the free electrons also carry energy, or the heat energy, from one place to the another place. So in this way also the heat conduction takes place. So by vibration, because of the vibration of the molecules, energy actually transfer from one position to the another position, and by the motion of the free electrons from one position to the another position, also heat conduction can take place. But this mode of or this particular mechanism is only possible in case of metallic solids, but in all cases these particular modes are in solids are available. Okay, so the first one is the vibration energy. Vibration energy okay, and the second point is the free electron. Motion of the free electrons also carry heat from one position to the another position. Now heat conduction mechanism in case of fluids are bit different. In case of fluids, actually what happens, even if the fluid is at a static condition, let us consider that fluid is in a static condition. Let us consider there is a bucket and some water is there in the bucket, so as if there is no motion of the water. Okay, so there is no bulk motion of the water, but within that water, at the microscopic level, there is always motion of the molecules of the fluids. In case of gases, these motions are atoms or the molecules are far distance away. In case of liquids, they are respectively closely attached, but this motion is there at the microscopic level always, even though the bulk motion of the fluid is not present. Okay, so this because and due to this random motion, always the molecules of the fluids are colliding with each other, and because of the collisions, basically heat is transferred. Okay, and that is basically the mode of conduction takes place through the fluids. So in case of liquids and gases, basically by the collision of the nearby molecules actually responsible for the heat conduction. Okay, so this is what is basically the mechanism of heat conduction. Now see the convection. Now first thing I like to mention is that we have seen in case of conduction that conduction can take place in both solids and fluids, but remember the convection takes place only in fluids. There is no conduction in solids. Okay, so only in fluids conduction takes place. That is the important thing that you have to remember. Now let us see the definition. This is the mode of heat transfer in which energy transfer takes place from one place to another due to the macroscopic motion of the fluid. This is a very important thing that you have to remember, that because of the macroscopic motion of the fluid, that means because of the bulk motion of the fluid, basically energy transfer from one place to the other place. And not only that, this is one part of the convection, and the other part of the convection is added on the energy transfer by conduction. So in the word convection, basically there are two parts. One is conduction in the fluid, along with that there is a part that is heat transfer because of the motion of the bulk motion of the fluid, which has been referred as the macroscopic motion of the fluid. It is not that motion that is taking place at the microscopic level. Okay, so it is the bulk motion of the fluid. Because of the motion, suppose this is a pipe and through the pipe some fluid is flowing, so that motion is basically responsible for the energy transfer from one place to the other place. So conduction along with this heat transfer because of the motion of the fluid is called advection. Okay, so conduction plus advection. What is this advection? Advection is heat transfer by the bulk motion of the fluid. Okay, and conduction, already you know, it is because of the microscopic level, because of the collisions at the microscopic level. In case of fluids, conduction takes place. So summation of these two, conduction and advection, is what is called convection. Okay, so this is what is basically the mechanism of the convection. One part is the conduction, and already you know what is the mechanism of conduction in case of fluid. And another part is the advection. In the advection, what happens? Because of the bulk motion of the fluid, heat energy transferred from one place to the another place because of the motion of the fluid. So for that, advection part is completely guided by the fluid motion. Okay, so that is why the fluid mechanics is closely related to the subject heat transfer. Okay, specifically when we are basically discussing with the convection study. Next, we see that what are the different types of convection. The convection in general can be divided into two types. One is forced convection, and another one is free convection, free or natural convection. We can also call natural convection. Okay, so what is forced convection? The forced convection, if the fluid motion that is required in case of convection, you know, if the fluid motion is created by some external agency. By some external agency means with the help of some fan, if we want to create the motion of the air or some gases, or with the help of blower we can do that, or with the help of pump we can create a motion in the liquids. Okay, so if this kind of external agencies are used to create the motion of the fluid, then the heat transfer in that case is referred as the forced convection heat transfer. Okay, and the free convection heat transfer is because of the because of the temperature gradient, the natural flow, because of the temperature gradient, what happens that density gradients occurs, and because of that basically fluid flow created. Okay, let's take one example, very simple example. You know that if you consider this is a vertical plate, suppose this plate is very hot. Okay, now what will happen if this is a hot, the air in this region will be heated up, and since when the air will be heated up, its density will become lower. So what will happen, this air will go up like this, and in this way air will go up, and after that there is no plate, again air will cool down and again come back, and again it will create a circulation like this. So this kind of a natural circulation takes place, and this is what is called the natural convection or the free convection. See here, there is no fan or there is no pump, nothing is there, there is no external agency, only because of the temperature difference actually density gradient created, and because of that this flow of air takes place. So here the flow is created in a natural way because of the difference of the temperature. So this kind of phenomena or this kind of study is under the natural convection or the free convection. Okay, now see what we mean by the radiation. First of all, let me tell you that for the conduction already you have seen either solid, liquid or gases through which conduction can take place. In case of convection, we have seen convection can take place only if it is a fluid, right? And remember, for the radiation actually there is even if there is no medium, in that case also the radiation can take place. Okay, so if you consider this is a body, and this body can be solid, can be liquid, can be gas, or it can be plasma, whatever that may be the state of the body, this will always emit radiation. Okay, and it is irrespective of that whether there is any material medium surrounding it or not. Okay, so this is what is the very important characteristics of the radiation. Now come to the definition. All the physical matter emits thermal radiation in the form of electromagnetic waves because of vibrational and rotational movements of the molecules and atoms which make up the matter. That means that suppose this is a matter, and within this matter it is consisting of the atoms or molecules, and these atoms or molecules actually vibrating. Okay, so and it can have the rotational motion also. So because of this vibration and the rotational motion of the atoms or molecules, it emits electromagnetic radiation. Okay, so that electromagnetic radiation, a portion of that electromagnetic radiation is called the thermal radiation. Okay, so the thermal radiation is a kind of electromagnetic radiation, and that radiation emits from the matter because of the vibrational and rotational motion of the molecules or the atoms it consisting of. Okay, so at any temperature it will emit radiation all the time. Okay, so this is what is the basic mechanism of thermal radiation, that if a body is at a particular temperature, it will emit thermal radiation, and this thermal radiation is nothing but electromagnetic radiation. And why this electromagnetic radiation is continuously coming out of the body? Because of the vibration and the rotational motion of the atoms or molecules it consisting of. Okay, so this is what is the basic mechanism that you have to remember. Now coming to the characteristics, there are very two important characteristics of the radiation. The first one is that if the thermal energy, rather if the temperature, if the thermal state or the temperature of the body is high, if the temperature of the body is high, then the amount of or the rate of thermal radiation that is coming out is more. So the rate of thermal radiation increases if temperature of the body increases. Okay, so this is the first important characteristics. And the second one is that for propagation of the radiation, it does not require any material medium. So for radiation to move from one place to another place, there is no requirement of the material medium. So no material medium is required. No material medium is required to transfer heat. To transfer heat means the rate of thermal radiation. Okay, so this is these are the very two very important characteristics of the radiation that you remember. So here we have seen a very basic a very brief description of the three mode of heat transfer. Okay, now we'll see one example again, and that example is of a solar water heater. So in the last lecture we have seen that some of the examples that engineers are working with, that means the example of a steam pipe, if you remember, and mostly in case of a steam pipe design, that means the thickness of the insulation design, it is the main mode was the conduction, right? Then we have considered one example that was for a condenser, and in that case mainly it is dominated by the convection heat transfer. Then we have seen another one for the heat treatment of a steel sheet, and for that we have considered a furnace, and that was example of radiation heat transfer. But remember, the examples are not always like this. In practical examples, most of the cases all kinds of heat transfer are in a combined situation. Okay, maybe in certain cases it is important to see that whether a contribution from conduction or a convection or a radiation may be insignificant. In that case we can separate that part, and we just consider or focus on the dominating mode of heat transfer. But here you can see one example where it is an example of a solar water heater. What is happening here, you can see these are the direct solar water heater panels. So sunlight, you can see, is coming. So sunlight is coming directly. So this is a kind of radiation basically which is coming into the covered glass plate. At the top you see the covered glass plate is there, and in the glass plate most of the rays that is coming in will be transmitted through the glass plane, because glass is very transparent. So let us consider the total amount of radiation flux that is coming is say G. Now out of this radiation flux which is coming G, let us consider a portion that will be absorbed in the glass plate or reflected by the glass plate, because some portion might be absorbed within the glass plate and some portion will be reflected, and the remaining portion will basically transmitted. If we consider the amount that will be transmitted, the fraction of which will be transmitted is tau. Tau is called the transmissivity of the glass plate. That means it is the fraction of energy that is transmitted. Then this G into tau is basically the amount of energy ultimately transferred through the glass. And below the glass plate, what you can see is that there is a black plate, you can see, and this black plate you can consider like this. This is the black plate. Okay, here is the black plate, and the energy when comes to this black plate, it will absorb that energy. So again, black plate can transmit, can reflect some of them, or it can absorb some of them, or it can again transmit some of them. But if we consider the amount that it will absorb is say alpha is what is the fraction of energy that is coming onto the black plate, the absorptivity is this alpha. That means it is the fraction that will be absorbed. So this much actually after transmitted through the glass plate comes into the black coated plate, and then if you just multiplied by the absorptivity of the plate, then this is the amount of energy that will be absorbed in the black coated plate. Okay, now you see that there are pipes, small tubes which are in contact with the plates. So definitely heat will be transferred from that black plate to the water which is flowing through these tubes. Okay, so the amount total energy that is absorbed in the black coated plate is this much, and this much energy is utilized to heat up the water through the tubes, and that is by the convection. Definitely the one part that will be by the convection, you can see, because heat will be transferred into this liquid. Since the liquid is involved, so it's a convection process. Okay, and you see at the bottom portion, it is basically insulated materials are there, because we do not want to lose heat, so some insulation is there, but still some heat will be conducted that region also. So some heat will be conducted, Q loss through the insulation by conduction, and what else? Definitely some of the energy will again radiate from that surface out. Okay, so this re-radiation will also takes place from the surface because of its temperature. So again, Q loss by radiation is also present in the situation. So if you see if we write this simple equation, that how much heat is this portion is basically the loss, and this loss portion contributed from the conduction and the radiation, and again here some air is also there, so some convection is also possible, so some loss may be by convection also. Okay, so this portion is basically the loss of heat, and this portion is basically the heat that will be utilized in the increasing the temperature of the water in the tube. So useful heat that you are going to get here. Okay, and this is basically the amount. So you see that in this example, conduction, convection, radiations, all these are involved. Okay, so for analyzing this kind of problem, like designing a solar water heater, or to find out what is the efficiency of the solar water heater, so definitely you have to consider all these modes of heat transfer. Okay, now let us see the laws of heat transfer. In the laws of heat transfer, there are two different kinds of laws. There are two different kinds of laws you can see. One is the fundamental laws, which are basically law of conservation of mass, Newton's second law of motion, and first law of thermodynamics. Second law of thermodynamics is also the fundamental law, but we in this particular course are not going into the detail of analyzing the second law of thermodynamics. Other than the fundamental laws, there are certain subsidiary laws in the heat transfer. We'll see that Fourier's law of heat conduction, Newton's law of cooling, Stefan-Boltzmann law, and other subsidiary laws of radiations are also there, like Planck's law, Wien's law, Kirchhoff's law. Okay, so when we'll go to the radiation, we'll see all these other subsidiary laws, but here we are starting with the fundamental laws. Okay, now law of conservation of mass. Now see, all the fundamental laws that we know, like conservation of mass or Newton's second law or first law of thermodynamics, all these laws are basically expressed in terms of system. Okay, so I hope by the time you know that what we mean by the system and control volume. So let us first discuss that, what is system and control volume. System and control volume. See, by system what we mean that what you have learned in thermodynamics is the closed system. So system means a specified or fixed mass. System means a fixed mass. Okay, so this is what we call a system. And control volume means what you have learned in thermodynamics is the open system. Okay, the same thing is what is the control volume. That means across that, if this is the control volume, then across that some mass can coming into it, okay, and some mass can go out of it. Okay, so across this control surface, mass transfer is actually allowed. Okay, so this is what is the basic difference between the system and control volume. And energy interaction in terms of heat and work is allowed in both the cases, whether it is a system or a control volume. Okay, in heat transfer course or in fluid mechanics course, we generally do not use this term closed. Okay, so whenever we'll write system, remember that means it is a closed system. That is implied always. Okay, so to represent the open system, we always use the term control volume. Okay, we never use the term system. System means it's a fixed mass. That means basically the closed system. Okay, so this is the basic thing. I am not going to repeat whenever we are going to use afterwards. Now all the fundamental laws that you know are basically defined for the closed system. All the laws you know. Let us consider the conservation of mass. What is conservation of mass? That is mass of the system, mass of the system is constant. Mass of the system is constant means basically this ddt of the system is equal to 0. So this is what is the law, that is conservation of mass. That is mass of the system is constant, that is not going to change. Okay, so here I have used the Lagrangian derivative to indicate that this is for the system that we have written. Anyway, I am not going into much detail of all these things right now, but it is known to you by the time, I hope, that mass of the system is constant. It is what is the closed system. It is what is the conservation of mass. So this is the first law. The second one is the Newton's second law. Okay, so what is Newton's second law? You know that force acting on the system, or the net force acting on the system, net force acting on the system is equal to net force acting on the system is equal to rate of change of momentum. Okay, remember this is for the system. This is very, very important thing. You have to understand that. All these are for fixed mass. Again, the first law of thermodynamics that you know is again ddt of E of the system. Remember, E of the system is Q dot minus W dot across the system boundary, or the net heat transfer on the work transfer of the system. Okay, so remember all these three fundamental laws that you have learned are basically defined for the closed system, or to be specific, system. Okay, but it is very important to represent this form of the equations to write in terms of control volume, because whenever we are going to deal with fluid systems, then it is required to express in terms of control volume. In case of solids, it is okay if the your if your system is only solid, in that case definitely there is no question of some mass is coming into it or some mass is going out of it. So you can apply the laws corresponding to system very well without any problem. Okay, so in case of solids there is no problem. You can use the form that you can see in the left hand side. I have written for the system that you already know. But if you are interested to apply these laws for the fluid system, where some fluid is coming into the control volume or some fluid is going out of the control volume, remember that fluid, when it is coming with some property like momentum, or it may come with some energy. Okay, so mass is coming into the system with energy, mass is coming into the system with momentum. Okay, so this is very important. So for that it is required to write this form of the equations for the control volume. Okay, so how to write, or what will be the form of the equations if we want to write for the control volume of the same equations? Okay, this is written, there is a relationship, but one thing you have to remember, all these three laws are the fundamental laws, so there is no proof of these fundamental laws. These are fundamental laws because there is no evidence that can prove that these laws are not correct. Okay, so it's a negative kind of a system, that if you have any example, any situation where you can prove that this is not correct, then that particular law will no longer be valid. But till now we have not got any situation where these laws are not satisfying. So these laws will always satisfy. Whatever be the situation, the laws will always satisfy. So these are fundamental laws. But the subsidiary laws we will see afterwards, and remember those may not be applicable all the time. It depends on, maybe it depends on certain materials, certain situations. Okay, but fundamental laws are always applicable in any situations. They are always valid. Now for the control volume, if we want to write these laws, then I have told you that there is no proof of this law. So what we basically now want to write, that using this Reynolds transport theorem, RTT, Reynolds transport theorem, this is a theorem by which basically we can relate the laws for the closed system, or the laws for the system, with the laws for the control volume, or the equation written for the system and the equation for the control volume. And the relationship is like this, that if you consider the change, so if you have problem why I am writing this capital D, right now maybe you are not getting the point that why instead of a small ddt I am writing ddt. Actually I just want to mention that these are all Lagrangian derivative, that is why I have written in that way. But if you understand the basic thing, then you can also write in that way also. So ddt of mass, or any property, rather not mass, let us consider an extensive property, say P. Let us consider P is, sorry, let us consider say B. Okay, so what is B? B is an extensive property. P is some extensive property, and let us consider small b, or the beta, say beta is basically indicates the property B per unit mass. Okay, so beta is kind of this property per unit mass. Okay, if the mass is m, so beta is property per unit mass. So it is kind of a specific property, you can say also. Okay, so ddt of this B. We want to find out the how this property B is changing with time in a system, and how this is related to the change of this property in the control volume. Basically, I want to find this relationship, change of that property with respect to time with the change of that property with respect to time, but here it is in case of a system and here it is in case of a control volume. They are not equal actually, so they are equated with some added term, and that additional term is basically how much property is coming into the control volume through this mass and how much property is going out through this control volume with the mass. Okay, so basically if you consider within the control volume, if you consider that how much mass is coming into the control volume, say let us consider this is a control volume, and if you consider this is a surface through which suppose some mass is going out, suppose the velocity here is say v, and let us consider a very small area which is say dA, and then if you consider this is the unit vector, suppose unit vector of dA is eta cap. Okay, so tell me that what will be the mass flow rate which is going out through this area. So the mass flow rate that is going out through this area is definitely V dot eta cap dA into density of the fluid, where this is density. Okay, this is density. So V dot eta cap, basically what this indicates, V dot eta cap is nothing but the normal component of the velocity. That means if you divide this velocity into two components, one is normal to the area, another one is tangential to the area, definitely the normal component indicates that how much fluid is going out. Okay, so we have taken basically the normal component of the velocity. So V dot eta cap, this particular thing is nothing but the normal component of velocity of that area multiplied by that area. This is what is the volume flow rate that is going out, multiplied by the density is basically what is the mass flow rate that is going out, and then if you multiplied that with the beta, because beta is the property B per unit mass, then within that mass how much that property is basically going out, that you can find out. Now if you integrate over the whole control surface, suppose this is the area, let us consider this is the area through which fluid is going out. Okay, so you have to integrate this area throughout this control surface. So if you just integrate throughout the control surface where it is going out, suppose this whole area indicates the AO, this is basically the AO through which it is going out. Okay, then this is basically the property flux or the property rate of property that is going out from the control volume minus another part, and that is which is coming in. So coming in part is also very similar. simply beta rho v dot eta cap dA, sorry, over the control surface where it is coming in. Suppose AI is the area. You can consider, suppose this is the area through which maybe it is coming in, and if you add all this area, it is basically the AI. Okay, so the control surface through which the fluid is coming into the system. So this is basically the extra term that is, this is the extra term that is to be adjusted if you want to write this rate in case of a system and the rate of that property change in case of a control volume. So this particular Reynolds transport theorem gives an idea how the rate equations in case of a system and a control volume are related. So only extra terms are basically this one, and what this term indicates, that the rate of that property going out with the mass from the control volume minus the rate of that property how much going into the control volume. Okay, so this term is required to be adjusted. In this lecture I am not going to derive this particular relationship where from this is coming, but we are going to use these to derive all the relationships with respect to control volume. That means these fundamental laws with respect to control volume. Let us end this lecture here. In the next class or in the next lecture, we'll explain all the write all the fundamental laws in terms of control volume. Okay, thank you.